In the next few videos, we're going to start studying reactions that take place in aqueous solution. This is very important because essentially all of life takes place in a water solution, and therefore understanding those solutions is of primordial importance. Now, before we actually move on to very quantitative aspects of reactions in solution, we have to understand a little bit how those water solutions are formed. So in this video, we'll give an introduction for how to begin to think about what happens when you put something, a solute, in water. Now, water is a really good solvent, and the reason that it's a really good solvent is because of the following. When you look at the structure, okay, this water molecule is bent with an angle that is about 104.5 degrees or so. But very importantly, it turns out that this water molecule is polar. Okay, it turns out that the electrons that are being shared between the hydrogen atom and the oxygen atom in this bond, those electrons tend to be more attracted towards oxygen than they are towards hydrogen. Okay, so what that means is that there's an excess, a tiny little excess of negative charge around the oxygen atom, and a tiny little excess of positive charge around the hydrogen atoms. Right, so we can say that there's a partial negative charge there close to the oxygen, partial positive charge here close to the hydrogens, and this makes this molecule polar. Now, this has a lot of significance because it's this polar property that allows water to dissolve very many species. Okay, a common species that water can dissolve is sodium chloride, table salt. Okay, so let's try to think about how that solution process takes place. When you think about a grain of salt, when you actually take a look at the molecular level of that grain of salt, what you actually have is a lattice, it's a solid lattice in which you have alternating sodium and chloride ions. This is three-dimensional, okay, and we're not trying to represent here the perfect structure of this grain of salt, but suffice it to say that you have these chloride negative ions, sodium positive ions, very close to each other, so there are very strong attractions between these negative ions with these positive ions and the other way around. Right, so in principle, it would seem that breaking these ions when you put this in solution should cost a lot of energy. So how can water do this? Well, the reason that water can do this is because it's polar. So when you actually have that one of these ions dislodges from the grain of salt to end up surrounded by water, what happens is the following. You have a sodium ion, which is positively charged, but notice that water has a negative end, right? So the negative end of water can actually get close to the positive ion, and that is actually rather stabilizing, right? That is the positive end of water, this is the negative end. So this negative end can actually get very close to the sodium ion, that is stabilizing, okay? And there's actually very many water molecules that can actually go and do exactly the same thing. Right, so it is the addition of all of these stabilizing interactions between the negative end of water and that positive ion that can stabilize that ion in solution, and it actually makes the solution more stable than having a grain of salt surrounded by water with nothing dissolving. The same thing happens for the chloride ion, but in reverse. Right, the chloride ion, when it dislodges from this lattice, is negatively charged. Right, but the water has a positive end. Right, so that positive end of water, okay, this H, can actually come and interact favorably with this negative ion, okay, many times over. All right, so it's these interactions that that make the solution process possible, right? So it turns out that water is a very good solvent for ionic substances generally, okay, because you have this polarity property that can actually make the solution process feasible. Another property of water is that under Earth's conditions of pressure and temperature, water is a liquid. And the other thing that's important about water is that the liquid range is actually pretty large. Okay, you can go from 1 atmosphere of pressure from 0 Celsius all the way to 100 Celsius, and water will still be liquid. That is a lot of a large temperature range, which again makes life feasible on Earth. Okay, so that is a little bit of the properties of water. Why is it a good solvent, and how it can dissolve ionic compounds. Now, water not only can dissolve ionic compounds, it can also dissolve other compounds that are not formed by ions, okay, but that are polar. For example, if you think about alcohols, okay, it turns out that water is also a very good solvent for alcohols, especially their short chain. Alright, so let's see, here this water molecule, which we know it's polar. Okay, when we think about, for example, methanol. Methanol is an alcohol that is like this. CH3, CH, O, and then H. Okay, so notice that this methanol, it also has a an oxygen atom. And this oxygen atom is also close to a hydrogen atom. So the same effect that we have right here will happen in methanol. Right, so it turns out that the oxygen attracts the electrons of this bond more strongly than that hydrogen atom, and it has a positive end and a negative end. Okay, so this positive end and negative end can interact with the positive and negative ends of water, and again, that is quite stabilizing, and you can dissolve this type of substances that are polar without much trouble. However, water is not a very good solvent for apolar molecules. Okay, apolar molecules are those in which you don't have this type of partial charge forming. Okay, for example, methane. So if we replace this one by methane, by a hydrogen atom right here, you can't find any positive end, any negative end, and it turns out that water is not a really good solvent for those type of substances like oils and waxes and things like that. Okay, so again, this is kind of an introduction for water as a solvent and the type of substances that you can dissolve in water and which ones you cannot. Now, there's before we wrap up this video, we're going to introduce the concept of electrolytes and talk about weak electrolytes and strong electrolytes. Okay, so a way to characterize water solutions or aqueous solutions is to determine whether they conduct electricity or not. Okay, so substances or solutions of water that conduct electricity are called electrolyte solutions, and solutions of water that do not conduct electricity are called non-electrolyte solutions. Now, the key for conductivity of electricity is to have many ions present in solution. So ionic compounds like sodium chloride or potassium chloride and so forth, okay, when you make solutions of this type of species, okay, we know that water is able to break apart the ionic solid and generate free sodium plus ions and free chloride minus ions surrounded by water molecules, and those ions are now free to move around the solution. Okay, so if you put two electrodes in the solution, pass a current, they will actually conduct electricity. That solution will conduct electricity, and these are called strong electrolyte solutions. Now, there are some cases in which, even though you put an ionic solvent, it turns out that the electricity is not very strongly conducted. Okay, those are weak electrolytes, right? So a common example would be silver chloride. Okay, so silver chloride, when you put this in water, okay, it should generate silver plus and chloride minus. Okay, and again, all of these should be in water. So that is aqueous and aqueous. This is in water. Now it turns out that the interactions of silver and chloride are strong enough that water is not a really good solvent for this ionic solution. So even though you put this salt in water, there will be very, very few silver plus and chloride ions that form, and that means that the electricity is not very well conducted, right? So this is an electrolyte solution because it conducts electricity a little bit, okay, but it's a weak electrolyte. And that compares strongly with sodium chloride, in which 100% of the sodium chloride that you have in the ionic is dissolved as the free ions. Okay, so that would be a strong electrolyte, fully dissociated, weak electrolyte, only partially dissociated. The same type of weak electrolyte, strong electrolyte solution can be talked about with respect to acids. Okay, there's going to be acids, like for example, hydrochloric acid. When you put it in a water solution, it fully dissociates to protons and chloride. So that is a strong electrolyte. There are some acids that are weak. For example, acetic acid, right? So the acid present in vinegar, COOH. Okay, when you put it in water, this generates acetate, COO minus plus H plus. All right, so again, it turns out that this is a weak acid. Water is not a very good solvent for this type of acid, so there are very few acetate and proton ions, and that means that this solution will be a weak electrolyte. Okay, it will conduct electricity poorly. All right, so again, we're discussing here the properties of water as a solvent and how we begin to think about properties of water solutions in terms of conducting electricity, non-conducting electricity, and we have introduced the concept of electrolytes and non-electrolytes, weak electrolytes, and strong electrolytes as well.